Hello and welcome to the lesson number 6 of this course. I'm Mario Torrisi from the University of Catania, and in this course I'll show you the Grid and Cloud Engine, a core component of the Catania Science Gateway framework. This is the outline of this lesson. In the first part, after a brief introduction in the Science Gateway model, we will see the Grid and Cloud Engine. In particular, we talk about the job engine. Then we will see some code sample in how to use the Grid and Cloud Engine to perform application towards distributed computing infrastructure. And then we will see my workspace and my jobs, that are two other core components of the Catania Science Gateway framework. In the second part of this lesson, I'll show you an implementation of an example of Science Gateway developed using the Catania Science Gateway framework. And finally, I'll draw summary and conclusion. Okay, these pictures shows the Science Gateway model, and as you can see, we have several users from several organizations that have different roles and privileges. This user would like to perform their applications exploiting the distributed computing infrastructure's resources. In this picture, the distributed computing infrastructures are highlighted in the box on the bottom side of this slide. But to deal directly with the distributed computing infrastructure is often hard for several aspects. For example, because we have several distributed computing infrastructure middleware available, and each of those middleware have specific requirements. Furthermore, for the security mechanism adopted by the distributed computing infrastructure middleware that are often hard to the non-IT expert user. The Science Gateway paradigm aims to overcome these problems. And in particular, using the Catania Science Gateway framework, the developers can concentrate their effort on develop their domain-specific applications, exploiting a standard-based and middleware-independent Grid and Cloud Engine. We will see more in deep the SAGA Standard and the Catania Grid and Cloud Engine later during this lesson. This slide, as you can see, shows the Catania, the Grid and Cloud Engine schema. In particular, the Grid and Cloud Engine consists of two interfaces. The first interface used to communicate with several applications embedded in different Science Gateway, and another interface named the Distributed Computing Infrastructures interface, used to communicate with several e-infrastructure middleware. For example, with grid infrastructure, with local APC system, or cloud resources. Furthermore, the Grid and Cloud Engine have three submodules. The job engine, that is responsible for job management, the data engine that handles data on DCI, and both of them interact with the user tracking and monitor module that stores into the user tracking database each user interaction with the DCIs. Finally, the last item of the Grid and Cloud Engine is the e-token server. The e-token server is a standard-based solution that manages proxy certificate, proxy credentials. And those credentials could be used to access those infrastructures that adopt X509 authorization mechanisms. The SAGA Standard. SAGA is the acronym of Simple API for Grid Applications. SAGA is an open grid form specification, and it provides the basic functionality to develop application, tools, and framework that exploiting distributed computing infrastructures. It is independent of the underlying infrastructure details, and it consists of two main components: the SAGA core libraries and the SAGA adapters. The SAGA core libraries are the base system, the runtime, and the API packages, while the SAGA adapters consists of many libraries that provide seamless access to several kinds of distributed computing infrastructure middlewares. But SAGA is an abstract specification. We need a library that implements this specification and provides API to developers. There are several implementation of this specification. We have, for example, a C++ implementation made at the Louisiana University. We have also a Python implementation. But among the different implementation available, when we developed the Grid and Cloud Engine, we decided to adopt the Java one, named SAGA, and it was developed at the Computer Center of Lyon in France. And we adopt this implementation for its main advantages that are: it is middleware independent because it implements the SAGA standard and hides the infrastructure related requirements. It makes the extensions easy thanks to the adoption of the adapter, because to support new distributed computing infrastructure middleware is made easy by the adapter. And it is also OS independent. The job engine, that is a core submodule of the Catania Grid and Cloud Engine that we saw in the previous slide, provides a set of API to submit jobs towards DCIs. It is compliant with the OGF SAGA standard because it uses the JSAGA implementation of the standard. It is optimized to be used in a web portal that run an application server like Glassfish or Tomcat, but it could be also used in standalone mode. In this slide, I'll try to clarify the job engine architecture. The job engine consists of a job queue where job submission requests are queued, two sets of worker threads, a set responsible for job submission and another one responsible for check job status. Both of these worker threads set interact with the user tracking database to store the job status update. Finally, we have the monitoring module that can be used by a user to download job output when job complete and to monitoring the job status. Let me try to explain the job submission flow. In particular, when a user submits a job, a new job submission request will be put in the job queue. So, a thread from the job submission worker thread takes the job submission request from the queue and submits the job toward the DCIs. Once the job submission process is completed, a thread from the check status worker thread set start and run periodically to check the job status. And this thread also stores in the user tracking database the job status updating. The user can exploit the monitoring module to check the job status. And finally, when the job completes its execution, the check status worker thread set the done status in the user tracking database and download the output locally to the Science Gateway machine without any interaction from the user. The user can now download the output of his job directly from the monitoring, directly exploiting the monitoring module. The job engine has been developed keeping in mind the following requirements. It should be middleware independent, and it is possible thanks to the adoption of SAGA and thanks to the SAGA adapters, the support to new middleware can be easy. It should be easy to use by the developers. In fact, it exposes simple APIs to interact seamless with different kinds of distributed computing infrastructure middlewares. And it should provide scalability. This is because the job engine is able to manage several job submission requests in parallel, appending those requests to the job submission queue, and hiding all the delays due to communication with distributed computing infrastructure to the final user. Another important feature of the job engine is the performance, and because it is able to submit thousands of job submission requests toward DCIs, it also has a powerful accounting system fully compliant with AGVO portal policies, and it provides also mechanisms to guarantee that a job is correctly submitted, hiding infrastructure failures. The job engine provides also native support to special jobs, and in particular the special jobs that are currently implemented, currently supported by the job engine are the job collection. A job collection is a set of jobs that run in parallels. It provides also support to parametric jobs that are a set of parallel jobs, but these jobs share the same executable and have different arguments. And then it supports also one-on-one workflow. That is the simplest kind of workflow. A one-on-one workflow consists of two-level jobs. A first-level job that is the job collection, and a final collector, and a final job named collector job that collects all the output from the first level job and use those output as input of a new job. In this part of this lesson, I'll show you some code sample that you can use to exploit job engine API to submit jobs toward DCIs. In this case, we will see the code, this sample code show how to submit a simple job towards a DCI. The first step that you should do is define a set, in this case an array of resource manager, a list of resource manager. You have to define the job description, so the description of the application you would like to perform in the distributed computing infrastructure. In this case, in this example, I simply perform the hostname command. To define the job description, you can use the GE job description object. The GE job description object provides the set executable method to specify the executable of your application, the arguments that your application requires. Then you can set the input files if your application needs some file as input as parameters. Then you can specify the output and the error, that is the standard output and the standard error of the application. After you have defined your application description, your job description, you can now submit the job. To submit the job, you have to use the SAGA job submission object, and in this case the constructor accepts the description you have just defined. Then you have to specify the proxy certificate. In this case, this is required because the resource manager list I'm using require this kind of authorization method. And the robot proxy method accepts the host name of the token server, the port on which the token server listens, an identifier for the proxy certificate that should be used, and the other two string parameters are the VO name used by the resource manager and the role of the VO. The last Boolean parameter is just to specify if you would like to use an HTTPS connection between the eToken server host. After I set a user email, that is just and if you use a valid email address, when the job completes its execution, the job engine automatically notifies the user using this email. The last step is set the resource manager list we define above in this slide to the job submission object, and then using the submit job async method, we can submit the job towards the DCI. The job submit async method accepts the username, the name of the user logged in, the IP address of the portal of the Science Gateway on which your application is running, an identifier of the application you are performing, and a label that can be used to refer to this interaction in the My Jobs portlet that allows users to download and check job status. We will see the My Jobs next. Now I'll show you the code line needed to submit, for example, a special job. In this case, the code used to submit a job collection. As the same way we saw in the last slide, the first step is to define the resource manager. In this case, the resource manager are embedded in the infrastructure info object. Infrastructure info object is an object that stores all the information to specify the distributed computing infrastructure where your jobs will be performed. As you can see, after I defined two arrays containing the endpoint, the WMS endpoint, I set this WMS list, this list, to an infrastructure info object. The infrastructure info object constructor accepts an acronym as the first parameter is an acronym of the infrastructure. Then you can specify the BDAI of the infrastructure, the WMS list, the resource manager list that you defined before, And at the same way you see before, here we have the eToken server host, the port, the identifier of the certificate that should be used, the VO, and the roles used by the VO. After you have defined the resource manager list, at the same way you can specify the application description, the job description using DG job description. In this case, I simply perform a host name for the first job and the ls command for the second one. Then I specify the output path, the standard output, and the standard error. I set this description to an array that contains all the description for all jobs belonging to the job collection. And finally, creating the job collection object specifying the description we just defined. We can call on this object the job collection submission method that is responsible to submit the job collection towards the DCI. So, as you can see, with a very few number of code line, you can successfully exploit distributed computing infrastructure resources. In the last part of this lesson, I'll show you the My Workspace and the My Job application, and then we will see an example of Science Gateway implemented with the Catania Science Gateway framework live, and then I'll draw the conclusion of this work. So, if you plan to develop your own Science Gateway in your organization, you can simply reuse the My Workspace and the My Jobs portlet. The slide shows the My Workspace application. My Workspace, you can consider it like a menu, and in particular it provides a link to the My Jobs. It provides also a link to the My Jobs map that show where your jobs are running, and then provide also a link to provide support to your user. While the My Jobs portlet can be used by the researchers to check, to monitoring the job status and download the output when these jobs complete. As I told you before, I'm going to show you the Africa Grid Science Gateway. That is an example of Science Gateway developed using the Catania Science Gateway framework. And let me go to the browser and I'll show you it in action live. Here we have the application menu, where, as you can see, we have several applications from several domains, research domains. For example, under life science and healthcare domains, we have GROMACS, Cluster W, and so on. And for example, I can show you the infection model. The infection model is an example of application ported in the context of the Sci-GaIA project that allows you to perform an infection model developed using the Repast Symphony agent-based simulation framework. And a user can access the run page clicking on the run link, and from the run page, after a brief introduction on how to use this application, a user can select a predefined experiment from a set of available experiments. For example, now I can select the experiment 3, and using the submit button, the Grid and Cloud Engine submit these jobs toward the DCI, and in this page we can see that we have successfully submitted our jobs. Using the My Jobs portlet that can be accessed from the My Workspace, you can see that we have a running interaction from the table, while the other two entries of this table are interaction that I performed before, and this interaction has been successfully completed. So, clicking on the folder icon on the right side of this table, you can download the output directly on your system and use the output as you want. So now I'm going to draw some conclusion. As you saw, the Catania Grid and Cloud Engine provide to developers a powerful set of API to port application on infrastructure in an easy way. The same code can be used to perform application towards different kinds of distributed computing infrastructure middlewares. And several applications has been successfully ported to several kinds of application from several research domain has been successfully ported to Science Gateway using the Catania Science Gateway framework. Thanks for your attention. This slide is simply a recap. You can simply use this slide as a reference of the Catania Science Gateway framework. And thanks for your attention. See you in the next lesson. Bye.